Laws of motion, section E, gravitation. So these are the topics we're going to deal with in this video. Universal law of gravitation proposed by Sir Isaac Newton. So under this topic, we'll discuss about the gravitational force of attraction, the magnitude of this force, and the factors on which this force depends. We'll see what is universal constant and its unit. Then comes force due to gravity, the force with which the earth attracts a body. Because of this force, the body gets accelerated. So we'll discuss about acceleration due to gravity and also the relationship between universal constant and acceleration due to gravity. Then comes free fall of an object, mass and weight, and the relationship between mass and weight. Universal law of gravitation. According to Newton, the force of attraction acting between two bodies is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. And the force is acting along the line joining the two particles. So here we have two mass particles m1 and m2 separated by a distance r. That is, the distance between m1 and m2 is r. So here we have F12 equal to F21, but they are acting in opposite direction and also along the line joining the two particles. So the force of attraction, the magnitude of the force of attraction is equal to G into M1 M2 divided by R square. That is, force is directly proportional to the product of the masses and inversely proportional to the square of the distance between the particles. So F is inversely proportional to R square. F is inversely proportional to R square, or F is directly proportional to 1 by R square. Here that means when R increases, the distance between the particles increases, the force of attraction decreases. And when R decreases, the force of attraction, obviously, it increases. That is, when the two particles are, it is being separated or it is being moved apart away from each other. Obviously, the distance r will increase and the force of attraction between these two particles will decrease. In the universe, each mass particle attracts other mass particles, and the force of attraction between two particles because of their masses is called gravitational force of attraction. For the magnitude of this force, Sir Isaac Newton proposed a law known as Newton's law of gravitation. And according to this law, the force of attraction between two bodies, it is directly proportional to the product of the masses and it is inversely proportional to the square of the distance between them. That is, F is proportional to m1 into m2 divided by r square. So let us understand from this diagram. There are two mass particles m1 and m2. So r is the distance of separation, that is the distance between the particles m1 and m2. So here we have the direction of F12, force F12 on mass m1. It is acting towards m2 along the line joining the masses. Similarly, the force F21 on mass m2 is towards mass m1 along the same line. So we have F12 to be equal to F21. They are equal in magnitude, but they are opposite in direction. Force being a vector quantity, vector F12 is equal to minus vector F21, which means the two forces F12 and F21, they are equal in magnitude, but they act in opposite directions. So coming back to the law, F is proportional to m1 m2 divided by r square. Here, to remove the proportionality symbol, we introduce a constant. A constant has been introduced known as the gravitational constant. So we have F is equal to G into m1 m2 divided by r square. So now let us find the unit of the gravitational constant G. So from this formula we have G is equal to F into r square. We take r square left hand side. Okay, so we have F into r square divided by m1 into m2. So we're going to find the SI unit of G. So what is the SI unit of force? It is Newton. The SI unit of distance or maybe length, it is meter. So here it being r square, we have written m square, and then the SI unit of mass is kg. So we have the SI unit of G, the gravitational constant, to be Newton meter square divided by kg square. Newton meter square divided by kg square can also be written as Newton meter square kg power minus 2. The value of the universal constant G was found by Henry Cavendish. The value is 6.67 into 10 power minus 11 Newton meter square kg power minus 2, which is extremely a small force. According to the law of gravitation, the earth attracts each object around it towards its center, and the force with which earth attracts a body is known as force due to gravity on the body, and this force is acting vertically downwards. So we have the force due to gravity F to be equal to G into m into small m divided by r square. Here, as you know, G is the gravitational constant and capital M is the mass of earth, r is the radius of earth, and m is the mass of the object or a body kept on the surface of earth. So taking the value of m to be 5.96 into 10 power 24 kg and radius to be 6.37 into 10 power 6 meter, let us find the force of gravity on a body of mass m, which is equal to 1 kg, and this object is on the surface of earth. So substituting the values in this formula, we get the force due to gravity acting on the body is 9.8 Newton. That is, earth attracts a body of mass 1 kg by a force of 9.8 Newton towards its center. So as earth attracts an object towards it, the object also attracts Earth towards it by an equal force. Because the object is free to move, it starts moving towards Earth. But Earth, because of its inertia, large inertia, it does not move towards the object. Galileo found from his experiments that if bodies of different masses and sizes are simultaneously made to fall in vacuum from the same height, they all reach the Earth's surface simultaneously and with the same velocity. He also found that the velocity of a freely falling body does not remain constant. It increases at a constant rate. So we have the motion of a freely falling body, that is a body under the influence of the force of gravity. The motion of a freely falling body is a uniformly accelerated motion, and this acceleration is same for all bodies. The acceleration of a freely falling body, it does not depend on the mass of the body, its size and its shape. This acceleration is known as the acceleration due to gravity. So we define acceleration due to gravity as the rate at which the velocity of a freely falling body increases. And acceleration due to gravity is denoted by the letter G, and the SI unit is meter second power minus 2. And as you know, acceleration due to gravity, it is a vector quantity acting vertically downwards towards the center of Earth. Relationship between universal gravitational constant and acceleration due to gravity. The value of G is different on different planets and satellites. So let G be the acceleration due to gravity at a planet of mass m and radius r. By Newton's law of motion, we have the force due to gravity on a body of mass m on the planet F to be equal to mass into acceleration due to gravity. That is, F is equal to mg. By Newton's gravitational law, we have the attractive force F to be equal to G, that is gravitational constant, into mass of the planet into mass of the body on the surface of the planet, and square of the radius of the planet. So equating the equations, we get G m into m divided by r squared to be equal to mg. So m gets cancelled, therefore we get G to be the acceleration due to gravity, G to be equal to universal constant into mass of the planet divided by square of the radius of the planet. So we get G being a constant, mass of the planet being a constant. The acceleration due to gravity, it depends on the radius of the planet, that is, G is inversely proportional to the square of the radius of the planet. So this equation relates the acceleration due to gravity and the gravitational constant G. So the value of G on a planet, it depends on the mass and radius of the planet. So now let us see on the surface of Earth how the acceleration due to gravity, it varies. That is, the acceleration due to gravity does not remain constant on the Earth's surface. The value of G varies from place to place. When we have an object or a body at the equator, on the surface near the equator, so the distance r1, this is the distance between the center of Earth and the object. So here you can see Earth is not spherical, it is elliptical in shape. I mean to say it is flat at the poles and slightly bulged at the equator. So this distance r1, so I have r1 to be greater, so the acceleration due to gravity at this point will be less. When we consider an object at the pole, near the pole, the surface near the pole, we have the distance between the object and the center of Earth to be r2. So here you can see r1 is greater than r2. So compared to r1, at the pole we have r2 to be less compared to r1. So obviously we have the acceleration due to gravity to be greater near the pole. So I mean to say on equator, it is the acceleration due to gravity is slightly less as compared to that at poles. The mean value of g, that is acceleration due to gravity, on Earth's surface is 9.8 meter per second square. So at altitudes above the Earth's surface or at depth below the Earth's surface, the value of g, it decreases. Similarly, the acceleration due to gravity on the surface of Moon will be 1/6 the acceleration due to gravity on the surface of Earth. So we have the acceleration due to gravity on the surface of Moon to be 1.6 meter per second square, and the acceleration due to gravity on the Earth's surface, as I already mentioned, it is 9.8 meter per second square.